14 is basic matrix operations, and for Math 1324, exam 4 review. The session will be recorded so that you may come back to it later if you need, and so others who may have missed out on today's event will be able to come and watch it. Thank you. Also, this event will provide the handout passport points. The code will be posted on the chat at the end of the session for the handout passport points. In addition, the link for the 1324 room will be posted in the chat. So now at this time, please mute your microphones for best time experience. Otherwise, the feedback could interfere with information we will be sharing today. Without further additions, here's our presenter for today, Professor Alberto Isasi.
Hello, everyone. Welcome to Friday, our last Friday Happy Math Hour for the summer. If you are in 1324, they put the chat link there in the chat. And so today we're going to go ahead and cover basic matrix operations and a little bit of the rest of the sections in chapter 8. And so we'll get started here. So for chapter 8, we're going to look at a matrix. What is a matrix? So basically a matrix is a rectangular array of numbers, and it looks something like the picture I have here. And if you notice here, this is the actual definition, but basically what I want to highlight here is that this matrix is made up of rows and columns, and the rows are going to be your horizontal rows here, and the columns are vertically going up and down. The numbers inside are called elements or entries. And if you notice, each of these numbers inside, like A11, these numbers here tell you what position they are located in. So if we look at A11, the first number 1 just means that it's in the first row, second column. So if I look at A32, that just means that that's in the third row, second column. The way we identify a matrix is we use capital letters to name the matrix, but we also want to see how big it is. And so instead of saying how big is the matrix, we use the word find the order or the size. And so the way we identify the size is by looking at how many rows it has and then how many columns it has. So in this example, we would say it's an M by N. M is going to represent your rows and N is your columns. And so if we look at this example here, we have this matrix here. It's a 2 by 2 because it has 2 rows, 2 columns. And this is called the square matrix. A matrix with 1 row and 2 columns is called the row matrix. And a matrix with 2 rows, 1 column is called a column matrix. And then this last matrix is a special matrix. Notice that it has ones on the diagonal and everywhere else is a 0. If we see this matrix, this is called the identity matrix. And so the size of the matrix, again, we represent them by rows and columns. So here we have a few examples. Determine the dimension of each matrix. And so the first one, it only has one number. And this number is located in the first row, first column, since that's all that there is. And then this next matrix is going to be 1 row. And then we have 4 columns. And then the 0 matrix here has 2 rows and 2 columns. And then the third one has 1, 2, 3 rows and 2 columns. So if we were to match them with the sizes over here, then this is what it would look like. Okay. Now, the augmented matrix is used to help us solve a system. And so basically an augmented matrix is taking a linear system from chapter 7 and we write it into a matrix. And so if you notice here, my first equation, the coefficients are 3 and 5. And so those coefficients would be on the left side of this matrix. And then the constants are going to be on the right side. And so when we write it on paper, usually we put a bar here to separate your coefficients from your constants. But sometimes if you use a calculator or if you use the computer, you're not going to see this line but just know that it's there. And then the second equation is the coefficient of x is 1, the coefficient of y is 4, and then we have a negative 10. And so if we wanted to write the augmented matrix here, let's see what it would look like. So all my variables will be on the left side. My constants will be on the right. So we start with the first equation. So in front of x, we have a 1, a 3 for y, and a negative 1 for w. And then we have 9 for our constant. Okay. And notice here that I am missing a z. If I look at the second equation, I see a z here, but I don't see a z in the first matrix, in the first row. So I need to make sure that I use a 0 to replace that variable. Okay, so the next equation, I don't see an x, so I'm going to use a 0. And then y has a negative 1, z has a 4, w has a 2, and then my constant is negative 2. Then the third equation, x has a 1. There's no y, so we're going to use 0. Then we have negative 5, negative 6, and 0. Then we have 2, 4, and then we have our z is negative 3, and then w is 0 with our constant of 4. So the dimension, that's another word that we use for whenever they want to know the size. They might say dimension. So the dimension is going to be 4 rows, 1, 2, 3, 4, and 5 columns. So we say this is a 4 by 5 matrix. Okay, so it says write the system of linear equations to represented by the augmented matrix. So now we're going backwards. They give you this matrix. We want to know what the system is. Okay, so the first row here, my coefficients are 6 and 5. And they don't tell us what variables to use, but if they don't mention that, then we can just use x and y. So we have here 6x plus 5y, and then my constant would be 2. Then for the second one, we have 3x minus 9y is equal to 0, and that would be our answer. Let's look at this one here. So here we have x is 1 is for x, there's no y, and then we have our constant 4. And then for the second one, there's no x, and then our y is 1, and then we have 3. And so ideally what we want to do is we're going to be doing some work to take a matrix that looks like this, and our goal is going to be to make it look like this one here, so that once we have it written like this, then we can easily identify what x and y are going to be. Okay, so in order to do that, we're going to be using what we call elementary row operations, and there's really 3. One, you can change any 2 rows in the matrix. You can multiply a number to any row as long as it's a non-zero constant, and you can add 2 rows together. And so the symbols for switching the rows is going to look like this. And if you want to multiply by a number to any row, then it would be, in this case, we're multiplying the number c times this row. And then here we're just adding the rows together. Okay, so let's look at some examples here. Interchange the first and second row of the original matrix. So this is your original matrix. And all they want us to do is to interchange the first and second row. So my first row is 0, 1, 3, 4. So I'm going to make that my second row, 0, 1, 3, 4. And then my first row is going to be negative 1, 2, 0, 3. And notice that we didn't do anything to the last row. So we just keep that as it is. Okay, the letter B says multiply the first row of the original matrix by a half. And so here we're going to multiply the first matrix. Let me go ahead and use my pen really quick. Okay, so we're multiplying by a half. Oops. Let's try that again. And we got the wrong one. So we want to multiply by a half. And so what we're going to have here is we're taking a half here. I need to take the background off. Well, for now, so we have 1/2 times 2. And let me start over again. And remove this. Okay, there it is. So we're going to take the half and multiply it into the first number, and then the half into the next number, and then the half into 6, and the half into -2. So if we do that, then we're going to have, let me just go back so we can, or let me erase this really quick. All right, so we have 1/2 times 2, then we end up with 1, right? So 1/2 times 2, and I thought I erased it, but it keeps going back. Okay, so let's try again. So 1/2 times 2 is going to be 1, and then 1/2 times -4 is going to be -2, right? So 1/2 times -4 is -2, and 1/2 times 6 is going to be 3, and 1/2 times -2 is going to be -1. And so the symbol that we're using here is 1/2 of row 1, and we're putting it back to row 1. So on the right side here, we have 1/2 times row 1. The arrow indicates that we're going to place it back in row 1. Okay, and we'll do some examples here in a little bit. The last one says add -2 times the first row of the original matrix to the third row. So here, what they want us to do is they want us to take the second row and they want us to take -2 and multiply it times the first row. So -2 times this first row. So -2 times 1 is -2. And then it says add to the third row. So -2 plus this 2 is going to give me a 0. Okay. And then if I go again, -2 times 2, that gives me a -4 plus the 1 will give me a -3. And then -2 times -4 is +8 plus a 5 will give me 13. And then -2 times 3 is -6 plus a -2 will give me -8. So notice that row 1 and row 2 stayed exactly the same because we didn't want to change those. Our goal is to change row 3. And so the way we read this right here is multiply -2 times row 1 plus row 3. Whatever answer you get, we're placing it in row 3. So these are examples of the row operations. And why do we need those? Let me just give you an example. So in chapter 7, they gave you systems of equations. We learned how to use substitution, elimination. And so now this is going to be another way to solve the same system. Okay, so if you have a system of equations, so this is a system of equations, and so this is a system of equations, then your first step is to write the augmented matrix. So here's my augmented matrix. Then we're going to use row operations. These are your row operations. And then our goal is going to be that our matrix has 1s in the diagonal and 0s everywhere else. Okay. Why do we want it to have only 1s in the diagonals? Because when we want to rewrite this, then this represents x, there's no y. So we have 1 is equal to x, so we would have x is equal to 6 divided by 23, and then y is 2/3, and then that would be your solution. Okay, so this process is called Gauss-Jordan elimination, and so we'll do a couple of examples. Let me go ahead and go to the next page. So here's our system. So the first thing we're going to do is remember what our goal is. So I always like to write it on the side of my paper just so I can remember what I want it to be. And then we're going to go ahead and write our system as an augmented matrix. So here we have 2 and 4, so that's 2 and 4. and then our constant is 8, and then we have 1, -1, and then 5. So if our goal is to have a 1 in this position, then you want to look at the number that we have. We have a 2, but notice that below it, I have a 1. So one of the row operations I can do is just switch the rows. And so I'm going to represent that by saying row 1, switch with row 2. And so now I have my 1 where I need it to be. Okay, so at least now we have our first step in our goal, which was to have a 1 here. And so now what we want to do is use this 1 that we just got and make anything below it a 0. So our goal now is to make this guy a 0. So if we look at our problem there, we have a 2 instead of a 0. And so what we're going to do now is go ahead and do row operations so that we can make this a 0. Well, in order to make the 2 a 0, I would need to add the 2 equations, but the number on top should be a -2, so that when I add -2 plus 2, it's going to be 0. So you might be asking yourself, but didn't we just change it to a 1? Yes, we changed it to a 1. But remember, if your ultimate goal is to change the 2, then your first row is not going to be affected. We're only going to use it to help us change that second row. So what we're going to do is we're going to multiply the first row by -2. We're going to add it to row 2, but our main result is going to end up in row 2. And so here, I always like to write row 1 because I know I do not want to change row 1. So I'm going to write it down so that it doesn't get changed. So now I'm going to take -2 times 1 is -2. I'm going to add it to the 2. So -2 plus 2 gives me 0. Then I go do the next one. -2 times -1 is +2 plus 4 gives me 6. And then the next one, -2 times 5 is -10 plus 8 is going to give me -2. So now in our goal, we have a 1 and a 0. And so, one of the questions that I get asked sometimes is, well, let me just write this. Can I make this a 1 first? Can I make this a 1 first and then make this a 0? And then make this a 1 and then this a 0? And the answer is you could, but the problem there is that you might be going around in circles because you will you will undo what you have already done. So the best thing you want to do is make this first number a 1, make anything below it a 0, and then go to the next column and make that diagonal be a 1, and then anything above it a 0. And if we had more, then you would go to the next diagonal and make everything a 0. So that would be the order to go so that you don't end up undoing your work that you have already done. Okay, so now that we have our 1 and our 0, next our goal is to make this 6 a 1. Okay, so if you want to make something a 1, then we can multiply here by its reciprocal. So 6 times 1, 6 will give me a 1. In other words, we're just dividing by 6. So I'm going to go ahead and multiply 1, 6 times row 2, and then whatever answer I get, I'm going to put it in row 2. So the first row is not being changed. So we're going to leave that first row the way we have it. It's right here. So 1, 6 times 0 is 0. 1, 6 times 6 is 1. And 1, 6 times -2 is -1/3. So now we have our 1, we have a 0, and we have our 1. So that's part of what we needed to have, 1, 0, 1. Now we need to make that number above the 1 be a 0. So if you notice here that the 1 and the number on top is opposite of it, it's a -1. So really all we have to do is add the 2 rows. So we're going to add row 2 plus row 1. And now we're trying to change row 1. So my answer would be placed in row 1. So row 2 is not going to be changed, so it stayed the same. And now I have 0 plus 1 is 1. 1 plus negative 1 is 0. And negative 1/3 plus 5 is going to be 14/3. And so your solution, we write it as x is equal to 14/3 and y is equal to negative 1/3. So please ignore those extra x's and symbols there. I think the PDF just didn't read the math terms there. But your answer is x is 14/3 and y is negative 1/3. Okay, so again, this is just 1/3. Okay, so again, this is just another way to solve this system. The good thing is you do also know the chapter 7 methods. This is a chapter 8 method. And so you might be wondering, like, why do we have another method? So if you have bigger systems, then matrices would be easier to work with. Let's try one more. So here I have -3, 6, 4, and -4, 22, and -28. It says to solve the system. And so first, I need to have a 1 here. Well, if I switch rows, it's not going to help me get a 1. So instead, I'm going to multiply -3 times -1/3. And then whatever answer I get, I'm going to place it back in the first row. So -1/3 times -3, +1. -1/3 times 4, -4/3. -1/3 times 22 is going to be -22/3. Okay. And then now that we have our 1, then we need the bottom one to be a 0. So in order to make it a 0, we need to multiply that 1 by the opposite number. So since I have a 6, I'm going to multiply the 1 by a -6. So let's go ahead and do that. So I'm going to multiply row 1 by -6, add it to row 2, and I'm going to put my answer in row 2. So row 1 is not going to change, so I went ahead and wrote it. And now we have -6 times 1 is -6 plus 6 is going to be 0. And then -6 times -4/3 plus -4 is going to be 4. And last, -6 times -22/3 is going to be 16. So we write our 16. So now we have our 1, we have our 0. Now I need this 4 to be a 1. So this 4, we're going to divide it by 4, or in matrices, we're going to multiply by 1/4 and then place our answer. So 1/4 times 0 is going to be 0. And 1/4 times 4 is going to be 1. 1/4 times 16 is going to be 4. So if you just wanted to know the solution, then notice here that we already know what this means here, right? This 1 is representing y. So here I can already say that y is equal to 4. And so if you have the system, then you can just back substitute and find your answer for x. But if you want to use Gauss-Jordan at reduce Gauss-Jordan, then our last goal is to make this -4/3 a 0. So to make it a 0, we're going to multiply by 4/3 and then add it to the -4/3. Okay, the second row stays the same. So 4/3 times 0 is 0 plus 1 is 1. And then the next one is 4/3 times 1 is 4/3 minus 4/3 is 0. Then the next one, 4/3 times 4 minus 22/3 is going to be -2. So our solution is going to be x is equal to -2 and y is equal to 4. Okay. Now, if you're allowed to use a graphing calculator, then there's a way to do this on the graphing calculator with 1 or 2 touches of your calculator. If we have time today, I'll show you how to do that. So the next part is examples from 8.2. Two matrices are equal if they have the same dimensions and the same entries. We can add them if they have the same dimension. Remember, dimension is just the size of the matrix. And the way we add them is we add the corresponding entries. We have something called scalar multiplication. And all that is a number that's being multiplied into the matrix. So every entry will be multiplied by that number. And then two matrices can be subtracted if they have the same dimensions. And we also subtract the corresponding entries. So we can look at it as A minus B, or if it helps, we can write it as A plus -1 times B. So for the matrices below, find 3 times A. So we'll do that one first. So 3 times A, 3 is your scalar. So we have 3. This is my matrix A. So every single entry in here is going to be multiplied by 3. So 3 times every single number. And so we get 6, 6, 12, -9, 0, -3, 6, 3, and 6. And that's all that the scalar multiplication is. For negative B, it's like multiplying -1 times your matrix B. So every number inside will be multiplied by -1. So 2 times -1 is -2. Then -1 times 0 is 0, and then 0 again. And then -1 times 1 is -1. -1 times -4 is 4. And -1 times 3 is -3. And then we get 1, -3, and 2 on our last row. And then letter C says to subtract. So in order to subtract, you want to make sure that the two matrices that you're subtracting have the same dimension. So the first one, A, has 3 rows and it has 3 columns. The B has 3 rows and 3 columns. So yes, we can go ahead and subtract them. And so for 3A, we already figured out what 3A was, right? It was down here. And we already know what B is, so we put them together. So we have 3A, that's what we got in this part. And then B is what we got here. So now to add, we're going to add the corresponding entries. And so what that means is whatever number you have in this first position, you're going to add it to this number in the first position. And then you go to the next one. So whatever is in here, you add it to this one here. And then the next one and the next one. And you keep going until you're finished. And so we end up with 6 plus -2 is 4. 6 plus 0 is 6. 12 plus 0 is 12. -9 plus -1 is -10. 0 plus 4 is 4. -3 plus -3 is -6. And so on. Okay, so that would be our answer for that. When you're looking at your WebAssign assignments, some of you maybe already experienced this, right? You're trying to add these together, but then maybe you don't have enough space or something happened. So these little green arrows here, if you click on them, it's gonna allow you to add rows or delete rows or add columns or delete columns, okay? So that's what these arrows are for, is to add more rows or delete them or add more columns or delete them. So here, if we wanna add these, do they have the same order? So A is a 2 by 3 and B is a 2 by 2. We're not able to add those. We're not able to add those because they don't have the same order. So on WebAssign, they want us to enter the word impossible. So make sure it's capitalized. They might count it wrong if it's not capitalized. And sometimes, excuse me, some of your instructors might want you to enter the word undefined, which is fine. So for the next example, solve for x and y. And so the only thing we know here is that these two matrices are equal. And I know that because of the equal sign. So if two matrices are equal, they have to have the same entries. In other words, if I have a 6 here, this has to be a 6. I have a -4, this has to be a -4. So I have a -3. That means that x has to be -3. And y is going to have to be 21. And so that is how we solve for x and y there. If we look at the next one, we have 18 and 18, 5 and 5, and then we have an x, and then we have a 2x plus 5, a 2 and a 2. So now it's a little bit different, but I know that this x has to be equal to the 2x plus 5. And so basically I can set up an equation. Same for y, 16 has to be equal to 5y minus 4. So now I can just solve for the equation. So if I subtract, if I subtract the 2x, I get -x equals 5. So x is going to be equal to -5. And then for y, same idea. I'm going to add the 4. So I get 20 is equal to 5y. So y is going to be 4. Okay, so solve for x in the equation here. So we have x is equal to 2a plus 2b. And so one of the things we can do first is I like writing it out. So I have 2, then my matrix A plus 2, my matrix B. Check the dimension. So this is a 2 by 3 and this is a 2 by 3. So I can proceed. Multiply 2 inside. So we get -6, 4, 6, -4, 0, 8. And 2 times each of these is 6, 4, -10, 10, 0, 6. Now we can add. So we have -6 plus 6 is 0. 4 plus 4 is 8. 6 plus -10, -4. 6, 0, and 14. And then we would enter our answer in there. Let me go ahead and go to the next one. So multiplication. So when you're going to multiply two matrices together, it's not like addition where the dimensions have to be the same. Instead, the first matrix, the number of columns, has to be the same as the number of rows of the second matrix. In other words, if they're right next to each other, the inside numbers here should be the same. The outside numbers, that's going to tell you how big your result is going to be. So if I multiply A times B here, the size of it is going to be M times P. Okay, so the number of columns in the first matrix has to be equal to the number of the rows of the second. So for example, if we have this right here, and we want to know if we can multiply, this is a 1 by 2, and this is a 2 by 1. So notice that the number of columns here is the same as the number of rows. Since they are the same, then yes, we can multiply. The outside numbers are going to tell me how big my matrix is. So whenever I'm done, this would be a 1 by 1, and that's going to be our solution. Okay, so how do we multiply? We're going to take this first row times the first column. We're going to take the first number times the first number and the second number times the second number and add them together. So 4 times 1 is 4. And then we're going to have 1 times 2 is 2. So 4 plus 2 is going to be 6. And that would be our answer. Okay, let's look at B. Here I have 2 rows and 1 column. 1 row and 2 columns. The inside numbers are the same. So that means that we can multiply. And the result will be a 2 by 2. So how are we going to do this? We're going to take the first row. So the first row is just the number 1 times the first number, which is 4. So 1 times 4 is 4. And then we're going to take that first row times the second number. So 1 times 1 is going to be 1. And now we add those together. Well, we'll add them right now, I guess. So yeah, so 1 times, so let me start over. So 1 times 4 is going to be 1 times 4. 1 times 1 would be 1 times 1. And then the next row, we go 2 times 4 is going to be 2 times 4. And then 2 times 1. So basically, you're going to take the first row with everything under the first column. And then the first row times everything under the second column. And that's what the position would be. So we have the last one is 2 times 1. If we multiply it out, 1 times 4 is 4, 1 times 1 is 1, 6 times 4 is 8, and 2 times 1 is 2. So you only add if I had another number below 4, then that's when we would add. So in a little bit you'll see that example. So find a squared where a is 3, 1, negative 1, 2, negative 1, 2. If we want to multiply, that means a times a. So here's my a times a. The orders are 2 by 2. So this inside numbers are the same. So our result would be 2 by 2. So we're going to take the first row. Okay, so this is my first row. So it's going to be 3 times 3 and 1 times negative 1. And all of that together is going to be your first entry. Okay, then we go to the next one. 3 times 1 and 1 times 2. So that's going to be your second entry. And then we go to the next row. So negative 1 times 3, 2 times negative 1. That's going to be your third entry. And then negative 1 times 1 and 2 times 2. So if we multiply it out, 3 times 3 is 9 plus negative 1. And that's going to be 8. And then we have 3 times 1 plus 1 times 2. So 3 plus 2 is 5. And then negative 3 plus negative 2, negative 5, and negative 1 plus 4, 3. Okay, so it says solve the following operations. Can we multiply b times a? Well, b is a 2 by 2, a is 3 by 2. Notice that the inside numbers are not the same. So we say that this is impossible. And if you try to put this in your calculator, you'll get an error message. Okay, so that was multiplying. Now for the next section, you have the inverse of a square matrix. So basically, the inverse, if you multiply a matrix times its inverse, it's going to give you the identity matrix. Remember, the identity matrix is where you have ones across the diagonals. And so like this is a 3 by 3 identity matrix where you have ones across the diagonal and zeros everywhere else. And so if you see this negative 1 exponent, that means the inverse of that matrix. So let me go ahead and skip if you want to show that B is the inverse of A, we would multiply them A times B. And if you get the identity matrix, which you'll see here that we do, then it's going to be, so in order to be the inverse, it has to give you the identity matrix if you multiply A times B, but it also has to give you the identity matrix if you flip it around B times A. So if you multiply B times A, notice that you also get the identity matrix. If that happens, then we can say that they're inverses of each other. Okay. But how do we find this inverse? So there's different methods. I'm going to just focus on the first method here and the second method. But I do encourage you, if you like systems of equations from chapter 7, then this third option would be helpful if you like doing what you were doing in chapter 7. So here, one way to find the inverse, if you have this method works for any size matrix. It could be a 2 by 2, 3 by 3, 4 by 4, doesn't matter the size. So if you wanted to find the inverse here, then what we're going to do is we're going to attach the identity matrix. So here I attach the identity matrix, and then we're going to use row operations so that the first part of the matrix is going to be the identity matrix, and then whatever's on the right side would be your inverse. So in this situation here, I want to have a 1 here, which I do. So I don't have to do anything there. But now I need this negative 1 to be a 0. So if I add the two equations, 1 plus negative 1 is 0. 4 plus negative 3 is 1. 1 plus 0 is 1. 0 plus 1 is 1. So now I have my 1 and I have my 0. Here I already have a 1, so that's great. Now I need to make this 4 a 0. In order to make the 4 a 0, I need to multiply by its opposite, which is negative 4. And so let me just click on here. So -4 times 0 is 0. -4 times 1 is -4 times 0 is 0. And we're trying to change the first row. So let me start over here. So -4 times 0 is 0 plus 1 is going to be 1. And then -4 times 1 is -4 plus 4 gives me the 0. And -4 times 1 is -4 plus 1, -3. And -4 times 1 is -4 plus 0 is going to be -4. And so if you notice now we have the identity matrix here. So your inverse is going to be what's on the right side. So we say that our inverse is -3, -4, 1, and 1. So again, this method is good for matrices that are bigger than 2 by 2. If you have a 2 by 2, then the second method is going to be probably the fastest method to use because we have a formula for it. So if you have a 2 by 2 matrix, then the inverse, we can use this formula that tells us that we're going to have 1 divided by A times D. So you multiply A times D minus B times C. Then in the matrix, we're going to switch the D and the A. So I have A here and D here. We switch them. And then for B and C, we're going to switch the signs. So instead of positive, we'll have negative. Or if you had negative, then you would have positive. So we're going to do, I think it's the same one. So notice this is the same matrix. It's a 2 by 2, so I can use this formula. This part of the denominator, that's called your determinant, which we'll do some examples in a little bit as well. So here's my matrix. So here I have A, B, C, and D. So I'm going to have A inverse is equal to 1 divided by AD minus BC. And so we plug in these numbers, then we have 1 divided by A, which is 1, times D, which is -3, minus B, which is 4, times C, which is -1. And here I'm going to switch my A and D. So instead of 1, -3, I'm going to have -3, 1. And then for 4, I'm going to change the sign so it's positive. I write it as negative. And then the -1 is negative, so I write it as positive. If we simplify, we get -3 plus 4. And then that's going to be 1 divided by 1, which is going to be 1. So 1 times anything in here is going to be itself. Okay. If you happen to get a 0 in the denominator, then that tells you that there's no inverse. So you would just write no inverse. So let's try this one here. It's a 2 by 2, so I can use my formula. And we'll substitute the values. So we have 3 times 2 minus -1 times -2. I'm going to switch the 3 and the 2. So now I have 2 and 3. And then my signs here are going to change to positive, 1 and 2. So 3 times 2 is 6. And then negative is positive, 2. So 6 minus 2. And then let's simplify. So we get 1/4. And now we're going to multiply the 1/4 into each of these. So 1/4 times 2 is 2/4. 1/4 times 1 is 1/4. 1/4 times 2 is 2/4. And then 3 times 1/4 is 3/4. So 2/4 I can write as a half. Then I have a fourth, and then a half and a 3/4. So that's your inverse. Letter B. We can use the formula again for letter B. So we're going to have 1 divided by 3 times 2 minus -1 times -6. I'm going to switch my numbers here. So I'm going to have 2 and 3 and switch the signs, 1 and 6. So we simplify. 3 times 2 is 6. And then we have a negative. And then negative is positive. So we end up with -6. So we end up with 1 divided by 0. And 1 divided by 0 is going to be undefined. And so we say that the inverse does not exist, and we say that that means that it's not invertible, doesn't have an inverse. Now for something like this, find the inverse of a 3 by 3. Then for that one, you would have to attach. Let me get the pencil really quick. So you would have to attach the identity matrix. And then use the row operation so that you can change this side to the identity, and then the right side would be your inverse. Or if you're able to use a calculator, then you can enter this into the calculator. Okay, so why do we need this inverse for? So this is to help us again solve a system of equations. So now you have another way to do this, right? So the system of equations, if we know the inverse, if we multiply the inverse times b, b is your constant matrix, then it's going to give you your solutions. And so the way it would look is the following. So it says use the inverse matrix. So this is the inverse already to solve the system. So what we need to get from here is your A matrix is your coefficients. So notice that's just 1, -3, 3, and -8. So, and then B is going to be your constants, 4 and 12. And then X is just your variables, X and Y. Now, once you have your A, then you do the work to get the inverse. Well, in this example, they already gave me the inverse, so I don't have to do that. But if they don't give you the inverse, then you would take A and apply the formula to get the inverse. But once you know the inverse, then we can set it up with this equation. X is equal to A inverse times B. So X is X and Y is equal to the inverse, which they gave me, times 4 and 12. So now we can multiply this. So we have -8 times 4 is -32, and 3 times 12 is 36. So -32 plus 36 would be 4. And then we have -3 times 4 is -12, and 1 times 12 is +12. So that gives me 0. So my solution here is x equals 4 and y equals 0. So again, we do have all the other methods, right? We have substitution, elimination from chapter 7. We have the Gauss-Jordan from chapter 8.1. And now we have the inverse here. Let's try this example. So it says solve the system using the inverse. So again, you need the A first, 1, -5, 5, -24. B is your 27 and 128. Then you have your X and Y. So first you want to find the inverse. So we're going to have 1 divided by 1 times -24 minus -5 times 5. Switch the 1 and -24. Switch the signs for -5 and 5. Simplify. So we have -24 minus -25. And so that's just going to be 1 divided by 1 is 1. So my inverse is -24, 5 and -5, and 1. So now I have X is equal to A inverse times B. And so here's my inverse times B, and we can multiply. So -24 times 27 plus 5 times 128. That's going to be that first row here. And then -5 times 27, 1 times 128. So if we simplify, we get -648 plus 640, which is -8, -135 plus 128, which is -7. So our solutions are, let me go back, X equals -8 and Y equals -7. Okay, so here I have a bigger matrix, right? It says use the inverse to solve the system. So they already give you the inverse. And so here's my A matrix, which is all the coefficients. My constants are 0, 6, 3. So if I set it up, then I have my inverse, which is given to me, times my B is equal to, so let's see what we multiply it. So 1 times 0 is 0, 1 times 6 is 6, and negative 1 times 3 is negative 3. So if we add all that, we get 3. And then the next row, negative 3 times 0 is 0, 2 times 6 is 12, and negative 1 times 3 is negative 3. So 12 plus negative 3 is 9. And then the last one, 3 times 0 is 0. Negative 3 times 6 is negative 18. And then 2 times 3 is 6. So we get negative 12. Okay, so that was our solution. X equals 3, Y equals 9, and Z equals negative 12. Now in the last section, they have something called the determinant. And the determinant is just what we were doing with our, let me go back. This part here, the bottom part of the inverse that we're doing. So if we want to find the determinant of a 2 by 2, then the symbol that we use for determinant is you can either write the word or the DET with parentheses A, or you can use the absolute signs here, the two vertical lines. So if you see this or this, they're asking for the determinant. And then notice that instead of brackets, we're writing these vertical lines. And so all we're doing is multiplying A1 times B2 and then subtracting it from A2 times B1. And that's your determinant. So for A, here I'm finding the determinant of A. So I'm going to have 2 times 2, it's right here, and negative 3 times 1, which is right here. So 2 times 2 is 4. Negative and negative is positive 3, so we get 7. And then for letter B, we have 2 times 2, 2 times 2, and 4 times 1. So 2 times 2 is 4, minus 4 is 0. And then letter C, 0 times 4, and minus 2 times 3 halves. So 0 times 4 is 0. And then this would give me negative 3. So we answer is negative 3. So that works for a small matrix like 2 by 2. If you have something bigger, then we're going to go ahead and find the determinant. And this is how we would find it. So if you have a 3 by 3 here, then what you want to do is you can start with the first number and cross out that row and that column. And if we do that, notice that you're left with a little 2 by 2. And so if we take that little 2 by 2 and multiply negative 1 times 1 minus 0 times 2, then we get negative 1. Then we move on to the next one. So now I'm going to use the 2. I cross out the row and column that it's located in. And notice it produces a little 2 by 2. So 3 times 1 is 3, 4 times 2 is 8. So we end up with negative 5. And I keep doing this with every number. So now I'm looking at 1. So I cross that out and I have 3 times negative 1, 4 times 0. So that's going to be 4. Now that I'm done with the first row, I go on to the next row. So I start with 3. I cross out the row and column that it's located in. And then I have 2, 1, 0, 1. Find the determinant, we get 2. And then we go to the middle number. So now we have 0, 1, 4, 1. And then we go to the next number. And you keep going through the next row as well. So then you do the 4, the 0, and the 1. And so we end up with this these minors here, okay? So now we're going to take this result, these minors. Okay, so these are my minors. And we're going to apply the cofactors. So in this pattern for the cofactors, we have a plus, a minus, a plus, and so on. And so what you want to do is you want to take your minors, and we're going to take negative 1 times a positive. It's going to stay at negative 1. And then we go to the next one. We go to the next one. Negative 5 times a negative, that's going to change it to positive. And then the next one, 4 times a positive will stay positive. And then 2 times a negative would be negative. And then you keep going. So negative 4 times a positive, negative 4, negative 8 times a negative, positive 8. So once you have your cofactors, which are these right here, then we're ready to get our determinant. So the determinant is going to be the sum of the entries in any row after you multiply by the cofactors. So for example, if we look at the first row, we have 0, so I multiply it times the first cofactor. 0 times -1, 2 times 5, and 1 times 4. So this is 0, 10, and 4 is going to be 14. But I can choose any row. Let's say I choose the second row. 3 times -2, -1 times -4, and 2 times 8. And if I add all this together, I still get 14. And the same if you do the last row. They're all going to give you the same determinant. So the determinant of A would be 14, and that would be your answer. Okay, so Cramer's rule is yet another way to solve the system. And so really what's going on here is, at least for my classes, I show you the different ways you can solve a system. And then whenever I give you a test, I just say solve the system. You can pretty much use whatever you feel comfortable with. And so here is using the Cramer's rule. What you need is to get the coefficient matrix. So your coefficients, say A1, B1, A2, and B2. We're going to find the determinant of this coefficient matrix. That's what this represents here. And then we're going to find dx. dx, we're replacing the first column with the constants. And then for dy, we're going to replace that column with the constants. And we find the determinants as well. To get the answer, we're going to divide dx divided by d and dy divided by d. So this is what it looks like. Okay, so first, I always like to write this down just so I can have it. So my coefficient matrix is going to be the coefficients, so 4, -2, 3, and -5. We need to find the determinant. Okay, so 4 times -5, and then 3 times -2 is going to be -14. And then I need to find dx. So dx, I'm going to replace my first column. Instead of the a's, I'm going to have the constants. So my constants are 10 and 11. So I write 10 and 11. And then b is still -2 and 5. So now I multiply 10 times -5, 11 times -2, and I end up with -28. And then for dy, I'm going to replace my constant, my y's, with my constant. So instead of the b coefficients, I'm going to have the constants. And then we find the determinant, which is 14. And so now I can find x by dividing dx divided by d. So dx, we said, was 28, -28. And then d is -14. So we have negative will be a positive. And then dy was 14. And the determinant was -14. So we end up with -1. So my solution is x equals 2 and y equals -1. Okay, so if you would like to download this presentation, there should be if here where my mouse is, on top of it, you should see a box pointing down with an arrow pointing down. If you click on that, it'll allow you to download the presentation. And then there's also links to the YouTube channel, so you can always come back and watch the recorded session. So I'll go ahead and pass it over, and thank you for joining us this summer for Friday Happy Math Hour.
Thank you, Ms. Chuka, for the wonderful presentation. As Ms. Chuka said, if you'd like to download a copy of this presentation, you can definitely go to the right top corner and click on the box with the arrow going down while the presentation is still on the screen. We do want to remind you all about our previously recorded sessions, which are available to you on YouTube on the Tejano Virtual Events playlist. This session will also be available on that playlist later today. Also linked is a short survey to help us improve our Tejano virtual events sessions. Please do take a few minutes to fill out that survey. Before you all leave, I do want to share that the Tejano virtual events flyer for this session that we will have this today at 1 p.m. We will have the library services with Gail Sanchez. This concludes our Happy Math Hour for this semester. We do hope that these weekly math reviews were helpful for you and for your Math 13-14. And if you know of anyone that's taking this class next semester, please do let them know about the Happy Math Hour. We thank you all for coming in today, and we do hope that you have a lovely weekend. And if you have any questions, please feel free to use the chat box on your mic.